Good day, everyone. For today, our topic is all about engineered nanomaterials.
So we will be discussing this topic with the objectives of knowing the basic concepts of nanomaterials, engineered nanomaterials, their difference, the nature and uses of nanomaterials, nanotubes, and lastly, the preparation of nanomaterials.
For our first objective, we have nanomaterials.
Nanomaterials. These are natural, incidental, manufactured, and materials containing particles in an unbound state or as an aggregate and where, for 50% or more of the particles in the number size distribution. One or more external dimensions are in the size range 1 to 100 nanometer. This nanometer is equivalent to the diameter of approximately 500 atoms. Nanomaterials can facilitate the creation of small-scale products and processes at the nanoscale. The word anon is in nanomaterials came from the Greek word nanos, which means dwarf and 10. The word nano is used to refer to 10 to 9 or a billionth part of 1 meter.
Nanomaterials have existed in nature long before scientists could even imagine them. It began after the Big Bang when nanostructures were formed in the early meteorites. Our planet became an important source of natural nanomaterials. We have been using it for years, especially in the field of construction, medicine, and arts. Several historical artifacts owe their beauty to nanomaterials. The Lycurgus cup, a 4th century Roman glass cup, contains gold and silver nanoparticles that change color depending on the lighting. Stained glass windows found in many medieval churches also display brilliant colors thanks to nanomaterials inside the glass. During 1857, Michael Faraday discovered the first nanogold, which we may now know as colloidal gold. It is a liquid containing tiny particles of gold, what we now call as nanoparticles. Other facts about the history of nanomaterials is provided in this slide.
There are four classifications of nanomaterials according to their size: zero-dimensional, one-dimensional, two-dimensional, three-dimensional. Based on the image provided, we can depict that nanomaterials have three dimensions, with these being X, Y, and Z. Zero-dimensional having all three dimensions, X, Y, and Z, within the nanoscale range or are not dimensional outside the nanometric range, which is greater than 10 nanometer. Most commonly, zero-dimensional nanoparticles are nanomaterials are nanoparticles, while one-dimensional nanomaterials have two of the three dimensions, which is x, y, in the nanoscale range, but one dimension of the nanostructure is outside the nanometric range greater than 10 nanometer. One-dimensional nanomaterials such as nanofibers, nanotubes, nanohorns, nanorods, thin films, and nanowires are examples of needle-shaped nanomaterials. Two-dimensional nanomaterials have plate-like shapes with two dimensions outside the nanometer range, but one dimension, x, is at the nanoscale, which is between 1 and 100 nanometer. Coating and thin film, multi-layers, nanosheets or anon walls, free particles, tubes, fibers, ultrafine grained over layers, wires, and platelets are examples of two-dimensional nanomaterials. And lastly, three-dimensional nanomaterials or bulk materials are nanomaterials that are not confined to the nanoscale in any dimension or dimension range. All dimensions of a three-dimensional nanomaterials are outside the nanometer range or greater than 100 nm. But the bulk materials is made up of individual blocks that are in the nanometer scale, 1 to 100 nanometer. So three-dimensional nanomaterials have three arbita- arbitrary dimensions above 100 nm.
Moving on with our topic, we have the engineered nanomaterials.
Engineered nanomaterials are chemical substances or materials that are engineered with particle sizes between 1 to 100 nanometers in at least one dimension. It is well established that engineered nanomaterials derive many functional advantages from their unique physical and chemical properties. These novel properties have spurred tremendous interest in innovations across many industrial, commercial, and medical sectors. Examples of engineered nanomaterials include carbon buckyballs or fullerenes, carbon nanotubes, metal or metal oxide nanoparticles, and quantum dots, among many others. Some of these examples will be later on discussed in this presentation.
Engineered nanomaterials are fabricated in the laboratory or industry to obtain materials with specific features and applications. While naturally occurring nanomaterials form psychochemical processes, they are not directly created through human actions. And we have this called incidental nanomaterials, which is also known as anthropogenic or waste particles. They occur unintentionally because of man-made industrial processes.
For our next objective, we will be discussing the nature and uses of nanomaterials.
It is indicated that there are two factors responsible for the changes in nanoparticles, with them being A. Much larger relative surface per unit mass, and A. Predominance of quantum effects. A much larger relative surface per unit mass affects the changes in nanoparticles because it is responsible for the changes in reactivity, which may increase considerably with a decrease in the size of nanoparticles. As a particle decreases in size, a greater proportion of atoms are found at the surface compared to those inside. While the other factor affects nanoparticles because it induces changes in the optical, electrical, mechanical, chemical, biological, rheological, structural, or magnetic properties.
There are a lot of reasons why nanomaterials are small. Firstly, the smaller an object is, the larger its surface area per unit of volume. So nanomaterials have a higher proportion of surface particles that are less stable than their conventional forms, making the object more reactive chemically. Another explanation is the size of the structure is on the same scale as the wavelengths of the electrons. Quantum effects can become much more important in determining the material's properties and characteristics, leading the novel optical, electrical, and magnetic behaviors. These explanations are in accordance with slide 11, where we discussed the factors that changes nanoparticles.
Still under the topic of the nature and uses of nanomaterials, we have classified as the main carbon-based nanoparticles, inorganic nanoparticles, and other inorganic nanoparticles.
Carbon-based nanoparticles are a diverse group of nanoparticles that are primarily composed of carbon atoms. Under this slide, and onwards we will be discussing some main carbon-based nanoparticles. First is fullerenes, or also known as buckyballs, are spherical cages composed of carbon atoms which are bound to three other atoms. It contains 60 carbon atoms, although there have been reports of structures containing 28 to 1,500 carbon atoms with a diameter of 8.2 nanometer. Uses of fullerenes include antioxidants in personal care products, long-life batteries, temperature superconductor, and etc. Graphene is a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice. It is known for its exceptional mechanical strength, high electrical and thermal conductivity, and optical properties. Graphene has applications in recovery and in the flexible electronic components field.
Carbon nanofoils are hollowed cylinder in a hexagonal network of carbon atoms constituting a graphene nanofoil. It can have diameter as small as 0.7 nanometer. They are also thin sheets of carbon with a thickness typically ranging from a few nanometers to a few micrometers. They are composed of multiple layers of graphene stacked on top of each other. They are chemically stable and totally insoluble and light and flexible. Carbon nanofoils exhibit unique properties such as high thermal conductivity, mechanical flexibility, and electrical conductivity. They find applications in electronics, thermal management, catalysis, and energy storage.
Carbon nanofibers are cylindrical structures composed of graphene foils. They form a cone-shaped or cup-shaped structure. They have diameters ranging from a few nanometers to several micrometers and lengths up to several millimeters. Carbon nanofibers possess excellent mechanical strength, high electrical conductivity, and thermal stability. They are used in various applications including as additives in polymers, as catalytic media, and for gas storage, while carbon black are composed of partially amorphous graphitic materials which a substantial fraction of the elementary particles of nanometric dimensions, generally from 20 to 70 nanometer, mostly spherical and are bound in aggregates that interact strongly with each other to form agglomerates up to 500 nanometer. Carbon black has high surface area, good electrical conductivity, and excellent light absorbing properties. It finds extensive use as a strengthening agent in rubber products such as tires as well as inks and coatings.
Lastly, under the main carbon-based nanoparticles, we have the carbon nanofoams. They are islands of carbon atoms, typically from 6 to 9 nanometer, randomly interconnected to form a very light, solid, and spongy three-dimensional structure, which can act as a semiconductor. Carbon nanofoams display temporary magnetic properties. Carbon nanofoams can be produced through various methods, including laser ablation, chemical vapor deposition, and pyrolysis of organic precursors.
Under the classification in organic nanoparticles, we have our first example, which is metal nanoparticles. Under this, we have the gold nanoparticles, which are studied in particular and show an optical resonance spectrum in the visible range, which is sensitive to the environmental conditions, size and shape of nanoparticles. Their unique properties make it possible to envision a series of applications, particularly as optical markers for medical diagnosis or as cancer treatment agents. Another example is the nanometric silver. It is produced in large quantities and is mainly used for its antimicrobial properties. Other example includes nanometric platinum, palladium, and rhodium, which are used in catalytic converters, iron, nickel, and cobalt as catalysis. Particularly for the synthesis of carbon nanomaterials, aluminum as a fuel, iron as a doping metal, and copper in electronics. Gold, copper, and silicon and cobalt nanowires are capable of being electrical conductors or semiconductors have also been perfected and could be used to transport electrons in nanoelectronics.
Still under inorganic nanoparticles, we have the metal oxides. They are considered as the most common ones because they are produced on a large scale, are probably silica, titanium dioxide, and zinc oxide. They are used either natural or coated, mainly in the fields of rheology, plastics, and rubbers as active agents and additives, in sun creams, and as pigment in paint. Different metal oxides have appeared in varied forms, such as nanotubes, nanorods, nanoflakes, and etc.
Lastly, under inorganic nanoparticles, we have the quantum dots. They are typically composed of combinations of group 2 and 4 elements or group 3 and 5 elements of the periodic table. The number of atoms in quantum dots, which can range from 1,000 to 100,000, makes them neither an extended solid structure nor a molecular entity. They display unique optical and electronic properties at diameters of about 1 to 10 nanometer. Because of their quantum confinement, they can, for example, absorb white or ultraviolet light and remit it at a specific wavelength a few nanoseconds later. Depending on the composition and size of the quantum dot, the light emitted may range from blue to the near infrared.
Under the classification of nanoparticles, we lastly have the other inorganic nanoparticles, which are organic polymers and biological inspired nanomaterials. Organic polymers can be prepared in the form of nanowires, resulting in their use in the development of liquid phase or gas phase, ultrafiltration systems, or particularly as sensors. Some biodegradable organic nanofibers could be used in medicine for tissues, for tissue reengineering, or bone regeneration, or to control the release of drugs. They are considered to be the basic elements for the large-scale synthesis of organic and inorganic nanostructures of dimensions ranging from 1 to 100 nanometer and exhibit unique properties. While biologically inspired nanomaterials are highly diversified but normally include structures in which a biological substance is encapsulated, trap, or absorb on the surface. In particular, lipids, pep- peptides, and polysaccharides are observed, used as vector for the targeted transport of drugs, receptors, medical imaging chemicals, or nucleic acids. Also widely studied in the medical and pharmacological fields.
For our next objective, we will be exploring the topic of nanotubes.
So let's first define nanotubes. Nanotubes are cylindrical structure that can have lengths up to several centimeters and diameters in the nanoscale range, usually on the order of a few nanometers. It is also said to be a carbon allotrope that resemble a tube of carbon atoms. They are extremely robust and difficult to break, but they are still light because of their exceptional mechanical, electrical, and thermal properties, carbon nanotubes are one of the most investigated nanomaterials. Under nanotubes, we have what we call the carbon nanotubes. It represents cylindrical structures composed of rolled up sheets of graphene, a single layer of carbon, atoms arranged in a hexagonal lattice. And under carbon nanotubes, we have two primary types, this being the single-walled carbon nanotubes and the multi-walled carbon nanotubes. The single-walled consists of a singular layer of graphene, while the multi-walled consists of multiple concentric layers of walls of graphene.
Aside from the carbon nanotubes, we also have the boron nitride nanotubes and the metal oxide nanotubes. Boron nitride nanotubes have a structure similar to that of carbon nanotubes. However, it is composed of boron and nitrogen atoms, while metal oxide nanotubes is composed of metal and oxygen atoms. Boron nitride nanotubes demonstrate excellent thermal and aside from the carbon nanotubes, we also have the boron nitride nanotubes and the metal oxide nanotubes. Boron nitride nanotubes have a structure similar to that of carbon nanotubes. However, it is composed of boron and nitrogen atoms, while metal oxide nanotubes is composed of metal and oxygen atoms. Boron nitride nanotubes demonstrate excellent thermal and chemical stability, and it finds application in nanoelectronics and as reinforcement in composite materials. While, non, while, while metal oxide nanotubes applications span photocatalysis, sensors, and energy storage. Example, and composed titanium dioxide nanotubes.
For our last objective of the day, we will discussing about the preparation of nanomaterials and its manufacturing processes.
The, the preparation of nanomaterials are man-made nanoparticles engineered prepared to have the desired size, chemical composition, and a surface and charge properties. It can be produced in the liquid phase, mainly though through controlled chemical reactions. They can be prepared and or produced physically, chemically, and biologically via two main approaches, which is the bottom up and top down methods. Both will be discussed in the next slide.
As said in the last slide, the nanomaterials can be synthesized using two prominent approaches, this being the top-down and bottom-up approaches. In the bottom-up method, nanoparticles are constructed atom by atom or molecule by molecule. It involves the growth of nanoparticles from atomic-sized particles. Its advantage allows production of a greater diversity of architectures and often better control of nanometric state. In the top-down method, a large structure is gradually underdimensioned. Under nanometric dimensions are attained after application of severe mechanical stresses, violent cracks, and strong deformations. It involves the particle size reduction to nanosize. However, this process is only used for hard, brittle materials. It may not also not break down to the required particle size. Its advantage include capable of higher volume production, while its disadvantage is it makes control of the nanometric state a more delicate operation.
With that, this concludes our video presentation for the topic Engineered Nanomaterials. Thank you for listening and I hope you learned something.